Hi and welcome to the WinDbg Fundamentals Kernel Mode course here on Pentester Academy. My name is Pavel and I'll be your guide throughout this course. Let's start by discussing objects and handles. And so Windows is an object-based operating system. It's not object-oriented in the typical sense, it's just object-based. And so we have objects which are instances of some types. This is akin to looking at the object-oriented paradigm and saying we have objects that are of type which are classes. And so objects to types is the same as object or instances to classes in object orientation. Example object types include processes, mutexes, events, desktop files, semaphores, threads, and many other types of objects. So these objects reside in system space. They are always in kernel space, so they are never directly accessible by user mode. So from kernel mode, I can go ahead and find a pointer that is access the object directly if I want to. From user mode, I can only use something which is called a handle, which is an indirect way to access a kernel object. And that's because you can't really access a system address from user mode, and you want to shield the user mode code from any changes to this data structure in perhaps future versions. All these objects are reference counted, which means that if I hold a handle to an object, once I close the handle, it doesn't mean necessarily the object is destroyed. It really depends on other clients that may exist for this object. And so an object is just some data structure in memory. Part of it is owned by the object manager, which holds general information about the object, which we'll see in a moment. The other part is owned by the executive, that is by the kernel itself, and perhaps there's an internal kernel data structure which is managed by the lower level of the kernel space. So we know that we have an executive and a kernel, and so there may be some layering here, no more than 2 layers of course. In some cases it's just an executive object with no kernel, low-level kernel involvement. So what does the object manager hold about each and every object? There is an object name, so some object types can be named, and if so, that would be the name of the object. It's stored, if it does have a name, in something called an object directory, which is another type of kernel object really, but it's very similar to a directory in the file system, although it's completely in memory. And so the object can be named and put in specific directory. And we'll see a tool that shows us that in a moment. We have a security descriptor which indicates who can do what with the object, because every object can be protected. The object manager maintains the open handle count to know how many handles are open to the object, and also a list of handles to that object when we need to search or use one of these handles. And there's something called a pointer count, which is the number of kernel references to the object. And so the entire reference count of the object is the sum of the open handle count and the pointer count. When both of them are 0, that means the object is no longer referenced and the object manager will destroy it. And then there's a pointer to the object type, that's the class, so to speak, from which this structure was created. And so there's an object type, which is another object in itself, that gives generic information about the type of the object, which is not per instance but on a per type basis. So we have something like the type name. So a process is a type name, an event is a type name for event objects, and so on. Whether that's synchronizable, that means whether that object can be passed to functions such as kwait for single object, which means we can wait on some state changes on that object. And whether the object should be created in pageable or non-pageable memory. And there's some other stuff there, like how to actually handle opening and otherwise manipulating objects in a generic sense. And so if you want to see that, we can go ahead and look at these things using the debugger, but let's start with normal, or let's say standard tools. So first we have here a tool called System Explorer. This is one of my own tools. You can find that in my GitHub repository. And you can see here all the various types of objects supported on my system. You can see the name of the type object, its internal index, and how many objects and handles are currently open or exist for this particular type. So if we go ahead, we can even sort by objects, for instance, and we can see that file objects are by far the largest instances that we can find right here. So there are more than 1,000 file objects open at this time. And so a file object is a kernel representation for working with a device, where it could be also a file system file, but it's actually more generic than that. And there are 12,000 something handles to these objects, which means that there may be many colors here that are coming from the kernel, which don't use a handle but use instead a pointer, and that's perfectly fine. If you go ahead and sort by handles, we can see that the highest handle count here is for event objects, although the number of objects is a bit smaller than that. This means that there may be the case that perhaps there are several handles that point to the same object, which is also completely fine. We can also see that some object types don't have any handles to them. That typically means that these are objects that are only used in kernel mode, and so user mode, which is the typical client using handles, doesn't have a way to get handles to these objects, so we see 0 here. And so this is perfectly fine, and it's all good. So this is one way to get kind of a generic view of the system. Another thing we can do is look at the handles in a particular process. So I can go ahead, right click a process and look at the handles in that particular process. So these are all the handles within that process, and each handle has only meaning in the context of that process. And so the handle value itself is not global, it only has meaning in the particular process. You can see the object it points to and some other piece of information here which we'll not discuss at this point. And by the way, these features also of course available in Process Explorer. Let me open Process Explorer, which is more well known than my own tool. And so if I go ahead and look at any process, we can see here the list of handles to objects that are in this process. And each time I select a different process, the list here refreshes. If you don't see that, you should make sure that the lower pane is shown, and the lower pane can also show DLL, so you can switch between these here, and in this case we want to see handles. And by default you will only see the type and the name. If you want to see more, you can select columns here and select more items here, including the object address that you see here. This is the object address in kernel space. And by the way, by default, Process Explorer doesn't really show all handles in the process, but only handles to named objects, at least as Process Explorer sees that. If you want to see the entire list of handles, you will have to select this option, Show Unnamed Handles and Mappings. So now you see the real list of handles in that particular process. You can see that many objects don't have names, which is completely fine, by the way. So let's go back to seeing only name objects, just so we have a shorter list to work with. So any one of these objects is something I can go ahead and look at in the debugger. So if I double click one of these handles, we get the properties of the object itself. And so I can go ahead and copy the address, for instance, and then go to my debugger. I have a local debugging session here open, and I can use the object command to get information about a particular object. And you can see here that the object is in this address. This is the address I've given right here, and the type is a key. This is a registry key, and this is the address of the type object itself. And so all registry keys have the same type object, and this is the data structure itself. And I can go ahead and actually use that address to view the object type using the DT command. There's no special command for viewing type objects. We can just go ahead and view the actual structure, which is called _object type. And then I can paste in the address, and we'll get the type object information for all registry keys. You can see here the key and name here, which is part of this address here. And there's some other information here, such as, for example, the total number of objects and total number of handles, and the peak number of objects and handles. In fact, my tool here, object types, shows exactly this type of information that I can obtain using some native APIs. And so again, we see here the object and some information about the object, such as if it's in any directory within the object manager namespace, and the name of the object. In this case, that's the path to the registry. Notice this is the kernel view of the registry, starting always with \registry, and then in this case that's HK local machine, system current control set or control set 001, and so on. And then we see here something called the handle count and the pointer count. And so the handle count indicates there is just one handle open to that object, and the pointer count should indicate the number of kernel callers that hold pointers to the object, but the value here seems way too big. In fact, it is wrong. This is not the correct pointer count, and we can use the trueref command by clicking this link to have the debuggers locate the actual number of references. And the reason for that has to do with the way this information is stored, that it contains a sort of a counter of how many times the handle has been used, and that's combined with the pointer count. And that's why we get these weird values. And that's true of Windows 8.1 and later. And so eventually the debugger will figure it out and give us the correct reference count or pointer count to the object. You can see that real pointer count is 1. And this is the real result here. Another thing to see here is the object header. So every object has a header. We can go ahead and grab that pointer and use another DT command to look at the object header. There's a structure called object header. Let me do that. And we can see some other pieces of information that are common to all objects in the Windows kernel. One of them, for example, the security descriptor. In this case, it's null, but if it wasn't, we'll be able to see the security descriptor for this object. So let's select some other object which may be a bit more interesting in that regard. So here we see an event object. Let's grab that. So let me copy the address and go back to the debugger and use the object command again with this address. And so you can see that indeed this is an event object. The type is event. There is a different type object address here. We can see that the name is low memory condition, and it's actually in some directory object. And we'll look at that in a moment. We can see that the handle count is pretty big, and the pointer count again doesn't really make sense. We need to use trueref if we want to understand what the actual pointer count, or in fact the reference count to that object. Let me grab the object header in the meantime. I want to see what's going on in the header for this particular event. So let's give a few seconds to the trueref command to finish execution. Okay, so we see that the real pointer count is actually 205 and not that weird number. So again, let's look at the header for this object. So again, object header, and paste in that object header address. And this time we see that there is a security descriptor, so this object is protected to one extent or another. So we can go ahead and grab this address and give that to the SD command. So this SD command provides us with a view and kind of convenient view of a security descriptor if we can locate one. And if I try this out, I can see that the debugger is not really happy because it can't seem to figure out what's going on here. And the reason here is that the lower 4 bits on 64-bit systems and 3 bits on 32-bit systems are actually a bunch of flags. So I need to zero out this last digit, and then we get the actual security descriptor. So you can see here who the owner is, and this is the seed of the owner. In this case, this is the local administrator seed. This is one of those well-known seeds that is the case here. And you can see there's a DACL here, the discretionary access control list, which really indicates who can do what with the object. We can see here several access control entries. The first one is an allow entry for seed S110. That's the everyone group, by the way. And we have another allowed ACE type for the administrators group. and of course the mask indicates what kind of access we're actually allowing here. And so we won't get into that in this course. However, if you are familiar with security descriptors, you can look at them using the debugger. Another thing we've seen indirectly is that object names are stored with some form of path, and that path for really named objects is under the object manager namespace. You can see here, for example, there's a mutex here called zones cache counter mutex, but it is under the sessions1 base named objects directory. This is a directory kernel object that is managed by the object manager. We can view that using another sysinternals tool called WinDbg, and here's WinDbg. I'm going to rerun that with admin privileges, because then it can provide the full information that we can find within the object manager namespace. And here I can go ahead and look for sessions1 and base named object for that particular mutex. In this case, these are all kernel objects created by processes in session number 1. This is the purpose of this directory. So if I go and look, I can see that in fact this is the zones cache counter mutex right here, which is indeed in this directory. And so these directory objects are actually part of the object manager namespace and can be viewed with the object command. So I can go ahead and, for example, completely write this by using sessions1 base named objects as an example, and then we'll find that the object command is going to list all the objects within this directory object. So it's first going to search for that particular directory, and hopefully it will actually find it, and then it will start listing all the objects that are there. Each one has its own address, of course, and you can go ahead and click that to see more information using the object command once again. So you can see all the types of objects and the names of these objects, because the object manager namespace in this case only stores objects that have names in that particular hierarchy. And the thing that we see here, the hash, is just indicating the fact that internally this is stored within a hash table. So it's not going to be sorted by name or by type or anything like that. It's going to be hashed, and here you can see the various values for that hash. And so this particular list is quite long. I'm going to break it right here. So that's about objects, and we'll look at some other details in this object manager namespace later in this module. So what about handles? So we have the handle command, and with the handle command we can view handles either in a particular process or targeting a specific handle, or even the entire handle set in the system. So it depends really on how you operate the handle command. So if you want to get to this particular handle 5F4 here for this particular mutex and view information about it, how would you go about doing that? So the first parameter would be the handle itself, but you can't really just use the handle because this handle is only meaning in that particular process context. And so we actually first need to switch to the appropriate process. So let me first locate that process, and that process has the ID 2884. This is the process ID, so I'm going to look out for this one. So I can have the eProcess address for that particular process. So here it is, and then I can go ahead and switch to that process using the .process command. And now I can go ahead and try using the handle command with 5F4 and see if I get the correct handle result. And indeed I do. We can see that in fact this is the handle itself. The object address is this one. We can see it right here. The object command is automatically executed on that object address here. We can see that in fact the object name is zone cache counters mutex, and we see the directory object where it resides. And normally we see the handle count and pointer count like we do in any object command. And so the special line here is this one. That line indicates that this is a handle with this particular bit mask access. And so this indicates what kind of operations we can do using this particular handle. Okay, so now I can go ahead and do something very similar, but just show all the handles in that particular process. by just doing handle with nothing. And so you can see this is the current process, and then it starts listing all the handles within the process. Each one has its own index and points to its own object, or perhaps there'll be several handles pointing to the same object. That's fine as well. And you can look at the documentation for the handle command to see some more options that you can specify there. For example, looking at kernel handles, handles that can only be used by kernel mode. By the way, if you see that one of these objects is a directory object, then it further lists all the objects within that directory object. This is the normal behavior for the bang object command, which is invoked indirectly by the bang handle command in this case.